Okay, the last topic we're going to talk about in the probability and statistics unit is something called the normal distribution. And I'm going to start out with a little example here to help us see what the normal distribution is. What this tells us is that the height of adult males is normally distributed with a mean of 69 inches and a standard deviation of 7 inches. Okay, so this is going to use the mean and standard deviation to kind of lay out the heights of adult males. Now, let me explain to you real quick what the normal distribution is. It's kind of the shape of a histogram. So if I took like the height of all adult males and I put a histogram here, maybe it would look something like this. So these down here would be the heights, and this would be like the frequencies, which would be like the number of adult males. And of course these would be very high frequencies because there's a lot of adult males. But the normal distribution is when you have a symmetrical bell-shaped distribution that looks like this. So it's this curve here, and it's the shape of the distribution. So when something is normally distributed, it has this nice bell-shaped curve that's symmetrical, where you got a lot of the data in the middle, and this is where the mean is. The mean is in the center of this distribution. And then as you get, in this case, shorter and shorter, or taller and taller, the number of people get less and less. So way out here where you have really short people or really tall people, there's not very many people. Okay, but in the middle, near the average height, you got a lot of people. So when it has this bell shape to it, then we say that it's a normal distribution. And this is a very common thing to see in statistics. Oftentimes stat textbooks have normal distributions on the cover, and there's reasons for that, because there's very important distributions in statistics that are normally distributed. Okay, so in this case it says that the height of adult males are normally distributed with a mean of 69 and a standard deviation of 7. So what we do is instead of actually drawing out a histogram with actual bars, what we do is we just draw the shape of a normal distribution like this, and then we put the mean in the center. So in this case the mean is 69 inches. So this symbol that I'm using, this represents a population mean. And when I'm talking about the height of all adult males, I'm talking about an entire population. And so we use a different symbol. We don't use X bar. Okay, and then this symbol is this population standard deviation. Okay, so this symbol here represents the standard deviation. So this is a lowercase m in the Greek alphabet, and you would say mu, and this is a lowercase s in the Greek alphabet, and you would say sigma. So to me this looks like a cursive U, and that looks like a cursive O. That's just how I think of them. And so the standard deviation here is 7. Excuse me. So when you have a distribution that's normally distributed, pretty much all of the data is within 3 standard deviations from the mean. And this will be true for any normal distribution. So what you can do is you can go 1, 2, 3 and make these about the same length. And then you can do 3 below. So you can do 1, 2, 3. So you got 3 standard deviations above and 3 standard deviations below. And what I can do is I can find the height for each of these by taking 69 and then adding 7, and I would get 76. So 1 standard deviation above the mean would be 76. And then I could add 7 again, and I would get 83. And 83 would be 2 standard deviations above the mean. And then if I add 7 again, I would get 90 inches. And that would be 3 standard deviations above the mean. Now I could subtract 7 3 times. So I could take 69 minus 7, and I'd get 62 would be 1 standard deviation below the mean. Subtract 7 again, I would get 55, and that would be 2 standard deviations below the mean. And then I'd subtract 7 again, I would get 48, and that would be 3 standard deviations below the mean. Okay, and so every normal distribution, pretty much all of the data, not all of it, but pretty much all of the data is within 3 standard deviations from the mean. And this actually makes pretty good sense, because 48 inches is actually 4 feet tall. So if we're talking about the height of adult males, that's pretty extreme. There's not going to be very many adult males shorter than that. And when we get to 90 inches, this is actually 7.5 feet tall. And again, that is very, very tall. Okay, you don't get very many people taller than 7.5 feet. Okay, so this is actually pretty realistic. So, as it turns out, for every normal distribution, it doesn't matter if it's the height of adult males or the weight of newborn kittens or whatever, if something is normally distributed, then within 1 standard deviation, you actually have 68% of all of the data within that first standard deviation. And 68%, that's almost 2/3, or that's a little more than 2/3. So you already, within 1 standard deviation, you already have 2/3 of the data. Okay, now within 2 standard deviations, here, you actually have 95% of the data. So that, within 2, you pretty much have all of the data. Only 5% lie outside of that. And then within 3 standard deviations, you actually have 99.7% of all of the data within 3 standard deviations. So almost 100%. Kind of like I said earlier, pretty much all of the data is within 3 standard deviations. And there's only 0.3% that would lie outside of 3 standard deviations. And that it actually amounts to 3 out of 1,000. So you'd have to take a random sample of 1,000 people before you would find 3 adult males that are shorter than 4 feet, taller than 7.5 feet. So that's about right. That's pretty accurate. These are the extreme heights. Okay, but notice we don't ever say here that these tails ever touch the axis. They get closer and closer, but they never quite touch the axis. So there could always be a small fraction of a percent above or below a certain number, a very small fraction. But what you're just doing there is you're allowing there to always be someone taller than the last person. So someone's 8 feet tall, Guinness Book of World Records, someone could beat that someday. Okay, so we never let those actually touch, but the fraction of a percent that's outside of that is very, very small. Okay, so these 3 percentages are called the empirical rule. And that's just that you have 68%, 95%, and 99.7%. Okay, that these percentages will hold for every normal distribution. So I suppose it's called the empirical rule because when people look at a normal distribution and actually check those percentages, they're empirically verified, I guess. But it's kind of helpful to know these because then you know, for example, if someone lies above 2 standard deviations, you know that they're very extreme, right? Or if they're within 1 standard deviation, you know, they're in the middle 2/3 of the data. And so you can kind of know how a distribution, if it's a normal distribution, you can know how it's laid out by using the mean and standard deviation like this. Okay? Now there's one other thing that's going to play an important role here, and that's z-scores. So I'm going to call these actual heights. I'm going to call those x-scores. So the x-scores, those are kind of the actual values, the actual observations that you're observing in the population. So in this case, they're heights. But corresponding to each of those, there's a z-score. And the z-scores here, the mean would have a z-score of 0. And then these 3 would have z-scores of 1, 2, 3. And then these 3 below the mean would have z-scores of -1, -2, -3. And so the idea here is that the z-score tells you, so like if something has a z-score of 2, like 83 has a z-score of 2, it means it lies 2 standard deviations above the mean. Or if it has a z-score of -3, it means it lies 3 standard deviations below the mean. So the sign tells you if it's below or above the mean, and then the number tells you how many standard deviations away from the mean that it lies. And the reason we're going to use this is in the next video, got to pick this up, we're going to learn how to use something called a standard normal table. And on this table, there's going to be z-scores. And so we're going to look up z-scores, and it's going to give us percentages underneath the normal distribution. And so from this table, we could actually find these 3 percentages here. But we'll be able to find any percent we want underneath the normal distribution. But we're not going to be able to look up heights on here because there are no heights on the table. What there are z-scores. So for any height, we need to be able to find the z-score. So let me give you an example. Let's say like this is x equals 57. So 57 is between 55 and 62. So it's somewhere between -1, -2, -1. It's somewhere down here. And so the question is, what is this z-score here? So in order to find this z-score, we're going to have a formula that we call the z-score formula. So the z-score formula is going to be the x-score that you want to convert minus the mean divided by the standard deviation. So the example that we're going to use, my x-score is 57 and I want to convert that to a z-score. The mean is 69, the standard deviation is 7. So my z-score here would be 57 minus 69 divided by 7. Okay, and this is going to give me a z-score. Now, let's say I go to put this in and I go 57 minus 69 divided by 7. So if I do that, will I get the right answer? What do you think? Okay, think of the order of operations. Here, I want to subtract first before I divide by 7. On the calculator, it's going to follow the order of operations, and it'll divide by 7, 69 by 7, before it subtracts. So that is not going to be the right answer. So I either need to put parentheses around the 57 minus 69, or what I do 57 minus 69, and I hit equals to get the answer to that. And then I divide that answer by 7. and then you can see I get the z-score, and it is negative 1.71. And I'm going to always round the z-score to 2 decimal places. So that 4 means I round the 1 down to 1. Okay? Now I always round to 2 decimal places because in the next video we're going to see that when we look up z-scores on this table, the z-scores will be to 2 decimal places. So that's why we always round those to 2 decimal places. Okay? And that's the main idea behind the normal distribution. It's a distribution of observations like adult male, the heights of adult males. It has this shape. It has certain percentages, and pretty much all of the data is within 3 standard deviations. And so we can use these z-scores to mark off these. Okay, and then we can use a z-score formula to convert any height into the corresponding z-score. So now in the next video we're going to learn how to use the standard normal table.